Time to get started. I'm pleased to welcome everybody here to the Honors Lecture Series on Spaces and Places. As you know, I'm Dr. Philip Phillips, Associate Dean of the Honors College. It's been a great series so far. Our speaker and I were talking about the compression of time and how time passes very, very quickly. And we were talking about it on a larger scale, but it seems that in this class we are marching toward the end of the semester. I was looking at the calendar today, and we're getting much closer to the end. So that can be good. It can also be stressful for everybody. So I hope everybody is holding up well. In the dean's office, we're moving from thesis proposals to thesis defenses. So those are going on now, and you'll see on our social media students who defended their theses. And you'll see at the very end of this lecture series, Dean Weil and I will select 2 or 3 students to give presentations on their theses, their experiences, doing those theses or creative projects. And I think that is always a nice way to end the semester. But one announcement while I'm thinking about it. There are 2 papers in the class. You've already done the first reflection paper. The second one will be your final paper, and it will, I think I've given you an idea of what it's going to be. I'm going to give you another idea of what it's going to be, and then Nancy and I will post something on D2L probably in the next week. But essentially, the first one you reflected on your Beyond the Classroom experiences, or in rare cases, some alternative assignment. In this one, I'm going to ask you to think about 3 presentations that you heard over the course of the semester, that you will have heard over the course of the semester, that particularly resonated with you, and why. I want you to think about this. So I'm interested in what those presentations were about. So, you should speak knowledgeably, but I'm equally interested in how they resonated with you personally. So this is a personal essay. The other part of it is that I want you to think about the whole series and what the terms space and place mean to you. And in particular, what spaces or places are most meaningful to you. All right? I think I hinted at that at the beginning of the semester. I've wanted you to think about the terms, and some of the presenters have dealt more explicitly or less explicitly with the terms. But if you have them in your mind as you're listening, I think you've seen already how different people have framed their presentations to approach those two terms. So anyway, that's going to be the topic, and it will more or less appear in with a Dropbox in the D2L, and we'll do it in the same way that we did the first essay. We didn't have any problems with that. I hope that was pretty easy for you to submit your papers. Okay, so now we're transitioning. Our speaker today, Dr. Chuck Higgins, is a professor of physics and astronomy at MTSU. He also teaches honors courses here. He grew up in Huntsville, Alabama, and the nearby NASA Marshall Space Flight Center captured his interest in astronomy and space. He earned a BS in physics from the University of Alabama, Huntsville, and received an MS and his MS and PhD degrees from the University of Florida, where he studied the radio emissions from the planet Jupiter. He was a National Research Council postdoctoral fellow at NASA's Goddard Space Flight Center and is a founding member of Radio Jove, a NASA partner citizen science and education project. And no series about spaces and places would be complete without a scientist to come talk to us about space. So please welcome Dr. Higgins.
Thank you.
Thank you.
Oh, you're welcome. Thanks for the invitation. Oh, thank you very much. It's a pleasure to be invited, and I'm happy to talk to you. And I think I have an easy job because I get to talk about space, the noun, the thing. And this is the outline, and the title comes from, anybody ever heard of the astronomer named Carl Sagan? So he was pretty famous in the 60s and 70s, most famous for his series called Cosmos, where he had, it was on public TV, just phenomenal series on all things space and humanity and humanizing things in space. And the last episode was titled "Who Speaks for Earth?" And so that's the motivation. And then I'm going to talk to you and show you some pretty pictures. I couldn't not do that. And then pose a question for you. Just for fun, that's a picture that my student took last fall with the MTSU telescope. So here is the motivation. So Dr. Sagan, who grew up very concerned about the development of nuclear weapons. So that was, the Cold War was really raging in the 70s. And so that resonated with him. And so that was something he talked about in a lot of the series in this last episode. And these two pictures are not exactly the ones from his, it's a book too. You can actually buy the book called Cosmos, but the series too. But these two pictures are from this last episode, showing you the fragility of Earth. And so again, his concern for human survival in the event of global nuclear war, but then also thinking, who speaks for Earth if we were going to explore space? And in particular, if we might bump into somebody, something out there. Who speaks on our behalf? And so I was trying to be cute and clever and titled my talk then, "Who Speaks for Space?" But this is the motivation. And strangely, I'll start at Earth and talk about Antarctica. So this is before really the beginning of space travel and the exploration into Antarctica. And you see in 1957-58, actually geophysicists were wanting to go there and to explore Antarctica, and astronomers too, and people studying the atmosphere and the aurora, the ozone hole. That was a big topic of concern. And so that sparked this treaty, the Antarctic Treaty in 1959, to designate it as a natural reserve and, for scientific purposes only and peaceful purposes only. So no weapons, no army maneuvers or any of that. And you see, and they've updated it more recently, but it's held pretty well. And so the only people that are down there are scientists, and actually now tourists. They've got tour boats that'll take you down there. So the peaceful exploration of a piece of land on the Earth So think about that in terms of now the exploration of space. So we have to understand space, right? The final frontier. How big is it? How do we wrap our brains around things of this size? So I've got a few slides to kind of help you do this if you are not already familiar with this kind of thing. But so this is a scale size solar system. The distances are not to scale, obviously, here, but that gives you an idea of how big the planets are, how big things are relative to Earth. So that helps us scale things. How big is it compared to Earth? And these numbers, you know, they're just big numbers. Nothing we really need to remember, but we use scientific notation because the numbers get big. So you see the Earth size and then the Sun size, so you can easily do the math and see that the Sun is just a little bit over 100 times the diameter of the Earth. So 100 Earths would fit across the face of the Sun. And then by volume, 1,000,000 Earths would fit inside the Sun. And you see, you know, Jupiter is about 11 Earths in size and so on. So we can use Earth as a scale, but when you start exploring the solar system, now what scale? We can use meters or kilometers or something, but those numbers get so big, we're going to rescale things to this new unit called an astronomical unit. So the average Sun-Earth distance. And it's just easy. It's just an easy way to help us understand how far away, say, Jupiter is, or Neptune or something. So here's the inner solar system, and I said it for 5 minutes before class started. So this is what the solar system looks like if you were hovering above it about 20 minutes ago. And so we've got the inner planets all fairly close to the Sun, and then now when you scale up and bring in the outer planets, you see how the inner planets get pretty invisible. So now if we talk about Earth-Sun distances, astronomical units, you see, and rounding things here, it's pretty easy. Jupiter's about 5 Earth-Sun distances away. Saturn 10, Uranus, Neptune out to 30. And if you grandfather Pluto in, you can talk about Pluto as about 40 AU. And then we have several of our dwarf planets listed there as well. So the outer part of our solar system, only 40 or 50 AU from the Sun. So we've got spacecraft out there, and this is one that orbited Saturn. The Cassini spacecraft orbited Saturn. And can we turn down maybe these front lights, or do you need them for the video?
We can try.
Yeah, maybe just this front row if that's possible. Yeah, other way. Okay, that's a little better. So this is a...
Sorry.
It's okay. Yeah, that's better. So this is a picture, false color, image of Saturn from the spacecraft looking back towards the inner solar system. So Saturn is covering up the Sun. So it's a silhouette of Saturn in the beautiful ring system. What's really fun here is that Earth is visible and Mars is visible. So there's Mars right there. This is kind of bright. I'm sorry about that. Venus is right there. Mars is, you can tell Mars is a little reddish right up there. Everything else is stars. Earth from Saturn. That's what Earth looks like from Saturn. Now, this image is humongous, so I blew it up to full scale and then I just zoomed in on Earth there. can you see something else close to Earth? It's very tough to see it. I don't know if you can see it. You see that it's that little tiny thing off to the what is that, about 4 o'clock on the clock dial? You see that little bump there? That is what? The moon. Amazing. So we have sent spacecraft out to the far reaches of the solar system. Again, I wanted to give you a sense of scale and place here, earthly place. So the Voyager spacecraft launched in 1977. Before they had to turn off the camera to save energy, to save power, in 1990 they took a picture. They turned the spacecraft around and took a picture of the solar system from that distance, 40 AU. So Saturn was 10 AU, and now we're at 40 looking back at Earth. And these are all the frames that it took. And then the ones that are labeled there show you what the planets look like. If you're out at 40 AU looking back at Earth, and by the way, this experiment, it was kind of an experiment using the spacecraft, was led by Dr. Sagan, Carl Sagan. It was his idea to let us see humanity from this viewpoint. And so this is all the frames, and that's the frame for the Earth. Do you see the Earth over there? As he said, that's it. That's us. That's home. Earth, a mote of dust suspended in a sunbeam. So here is our. Oh, all right. One more slide. I'll come back to this. So, what is outer space? So, everybody take a breath. Okay. In that breath, in every square centimeter, cubic centimeter of volume, there are 10 to the 19th molecules. So a trillion is 10 to the 12th. And 10 million is 10 to the 7th. 12 plus 7 is 19. So 10 million trillion molecules. That's the density of stuff in the air that we breathe. Now you go about 100 miles up, and you're out of the atmosphere, and then now you're in interplanetary space, and you see the number of atoms, particles per cubic centimeter. And then if you go out of the solar system amongst the stars, that's interstellar space. So compared these numbers to this number, this is basically zero. Outer space is basically empty. Interplanetary, interstellar space is empty. And this is always a fun comparison. Avogadro's number, 10 to the 23rd. How can we imagine these humongous numbers? You really can't. If you had an Avogadro's number of, BBs, little tiny metal balls that you use in the BB guns, if you had Avogadro's number of them and you poured them out over the continental US, lower 48, that many, it would be a depth of about 4 miles. Unimaginable, right? And this is just to give you an idea. Space is so big. Space, capital S, right? So big. Okay, So maybe we need a treaty for outer space, modeled like the one in Antarctica. So now we're at 1967, and we have 117 plus countries signed on, and you see some of the provisions. Peaceful. It is free to use by all and is the province of all. And astronauts, whomever they may be, are regarded as envoys to mankind. This is kind of, I went down rabbit holes looking at this stuff, preparing for this talk. This is really, really interesting to think like this and come to some agreements how we're going to behave in space. So as I said, we've got many now spacecraft, the outer edges of the solar system. So the Voyager and the Pioneer are the four that are most distant. But you know, we have rovers on Mars and a spacecraft now orbiting Jupiter. So at the moment, this is the most distant spacecraft from Earth. Now 170 AU, 170 Earth distances, Earth-Sun distances. So that's how far the spacecraft has gone. How far has a human being gone? Does anybody know? How far have we sent a person from Earth? Let's go back. What's the answer? No, a human. That's a spacecraft at Saturn, but how far have a human being gone? Where have we set foot? The moon. Right? It's very humbling, isn't it? We have only stepped onto the moon. Well, let's keep going. So what's beyond all this? So here we have another scale. So this one's a little tricky, but it's kind of a logarithmic scale. So 10, 100, 1,000, and so on. So now we're going to talk about distances in a unit of we call light years. So the distance light travels in 1 year of time. So you see that's 10 to the 15 meters. Who cares what that number really is, right? It's unimaginable. Just for scale, that's 63,000 Earth-Sun distances. So now we're out to the interplanetary medium, and now we're out to the interstellar medium, and you see we come upon the first star from the sun, about 4 light years distant. If I take the sun and I shrink it down to this size, so it's about 60 billion times bigger than this thing. And I shrunk the universe down to this size, or let's say the Milky Way. Where is the next star? Where's the closest star if the sun were this big? You know, if I ask one of you to walk outside and walk towards, say, the edge of campus, the edge of town, we'll go south. Shelbyville. So I've got this one, and where's the next one? Huntsville, where I'm from. Birmingham. Mobile. The next rubber ball, the next star is you would have to walk to Mobile on this scale, right? It's just mind-boggling how far that is, isn't it? Space is really that, a lot of space. So now we're out to the stars, and we can study the stars and use telescopes either on Earth or in space. The Hubble Space Telescope or now the Webb Space Telescope take these incredible images of star formation regions, clouds, humongous clouds. So space isn't quite empty, is it? It's almost, but not quite. There are huge clouds out there that gravity can shape and make new stars. And that's what this is. It's called the Eagle Nebula. And you see, now we're at 7,000 light years. That's about 4 to 5 light years in size, the tower. And these little finger projections here, these are places where new stars are forming. So these would be the very tip of these little, those are solar system size things. A whole new star is forming here. So this is optical and a little bit of UV light. And so the Webb telescope is infrared light, so that allows you to kind of see through the clouds a little bit better. And it's a bigger mirror. And so you're seeing a lot more fainter stars in the background there. So, and I put them roughly to scale there side by side. Isn't that incredible? That's just one little place in space. Stars live their lives. This is another thing Carl Sagan was famous for, humanizing the evolution of a star from birth to death. Stars will die when they run out of hydrogen fusion or other types of fusion in the core of the star. And so this is the Ring Nebula, a gentle death of a sun-like star. Or over here, a much more massive star, when it forms, dies violently by blowing itself up and leaving a supernova remnant. So these are all clouds out there, but caused by a sun-like star dying and then a much more massive star dying. And then there's things left over in the center. That's a white dwarf, which is what our sun will become. And then in there, we have weird things called neutron stars or even black holes are made when stars blow up. Okay, now we can get bigger and talk about galaxies. So we have the entire Milky Way. Beautiful image, a composite image showing you the Milky Way stretched horizon to horizon. So we're in it, right? We're in the Milky Way, looking into the plane of this disk of galaxies. 100,000 light years across. And knowing where these stars are, measuring distances, we can figure out where we are in the galaxy. Everybody orbiting the center of the galaxy. The sun and us with it take about 210 million years to orbit the galaxy one time. That's a blink when you think of maybe geologic timescales or universe timescales. Okay, let's keep going. Other galaxies. Andromeda, our near neighbor galaxy, a mere 2.5 million light years next door on galactic scales. Matter of fact, so close that our galaxy and this one will eventually shake hands. Gravity is pulling us together. Another shameful plug for student work at the MTSU telescope. So that's a whirlpool galaxy, now 25 million light years distant. And then galaxies grouped together under gravity. So this is a cluster of galaxies called the Virgo cluster, 53 million light years distant. In the center of some of these galaxies are supermassive black holes. These words, it's tough to have a meaning to what a supermassive black hole is. Mass being how much stuff it's made up of, but what kind of stuff, we don't know. We don't know what's inside a black hole. We don't have the understanding yet. But this is what this galaxy looks like optically. And galaxies have, the bigger ones have 100, 200 billion stars in them, maybe trillion. And so in the radio, we now have the technology to take a picture using radio telescopes of what a black hole looks like. Incredible. And so this is light that is warped, bent around this black hole because of the warpage of space. All that just in the very tiny, tiny, tiny center of this humongous galaxy. And another radio telescope, you can actually see the jet of energy radiating outward coming from the energy of objects falling into this supermassive black hole. Yet bigger still, the Hubble Space Telescope did something incredible. They took a risk, they took a chance, and they took the space telescope, which of course is above the Earth's atmosphere, so we're not looking through the murky atmosphere, and it looked up near the Big Dipper, which is up out of the plane of the Milky Way galaxy, where there's not a lot of stars and dust and things to kind of get in the way. And it aimed at this tiny point, and it opened the shutter of the cameras for 10 days. Thinking they were going to find nothing, because they purposely pointed it at an empty place in space. And 10 days later, that's what they found. This tiny little region of space is filled with 3,000 galaxies. Distances out to about 12 billion light years distant. The foreground Milky Way stars you see here, and here. There may be one more in there somewhere, one up the edge there. There's another one. So 4 or 5 Milky Way stars, everything else is distant galaxies. Every little dot is now an entire galaxy. Not to be deterred, they did it again, pointing it in a different direction, downward. The extreme deep field, 5,000 galaxies, 13 billion light years distant. And just to give you a sense of scale, this is how big a section of space we're looking at with the camera. fun with numbers. How many stars are we up to now? So we've got 100 billion, 10 to the 11th stars, or maybe 1 trillion stars in a galaxy, but now there's 1 trillion galaxies. 10 to the 24th stars. Compare that to Avogadro's number, right? 10 to the 23rd. So we're right about there in terms of what we know is in space. And then if you extend this, you can approximate how many particles there are in the known universe. 10 to the 80th. You've heard of Google, right? That's where it comes from. A Google is 10 with 100 zeros behind it. Sorry, a 1 with 100 zeros behind it. Right? 1 with 80 zeros, 6 with 23 zeros behind it. How we represent these humongous numbers to understand space. Right? Are we the only ones exploring? So far, yes. We don't know of anyone else exploring. We don't have good enough proof. So these are other planets around other stars. Exoplanets, we call them. There's now 6,000 confirmed exoplanets. We're getting good enough to find Earth-sized planets. And we're getting good enough now to determine what kind of atmosphere are around some of these exoplanet worlds. So just a couple more here. So after the Outer Space Treaty, now we have a Moon Treaty. So the Apollo missions were in the late 60s, early 70s. So, we should probably have a Moon Treaty. Peaceful purposes only, right? Anyone can go there. Anyone can visit. This treaty created, an establishment to govern the exploitation of resources. How many people have signed this one? No, we're not going to do that. We're afraid that we don't want to be exploited. We don't want someone else exploiting. Maybe we want to exploit. So we better not sign it. So we can agree on Antarctica. We can agree on outer space. But now things are getting interesting. Mining asteroids, mining the moon, right? We don't want to give up potentially finding something valuable, so we're not going to sign. So that's where we are in the Moon Treaty. So one of the last people to walk on the moon in 72. I like. By accident, I found this image, so he's got a shovel digging. I think that's apropos here. So I'm going to leave you with this question and take your questions. So who should speak for space? I hope it's you and me to speak up. Right? We're the envoys, right? astronauts are going to be representing us as envoys to study. Boldly go, right? So we've got a few minutes here. I'll take questions, but I'm going to ask you one more question. If you had the chance, would you go to the moon? You'd only be there a few days. It'd take you a couple days to get there. You might be there a few days and you come back. Call it a week. How many of you would go on a spaceship, go to the moon? Yeah, I would go. Absolutely. Mars. Mars is, we're not sure, but it could be, if we carried a lot of fuel, we could probably do Mars, I'll say 6 months. But if we wanted to save fuel, it might be 2 years. 3 or 4 month trip to get there. And by the way, the planet's orbit, to save fuel, we'd have to wait almost 2 years before you take a 3 or 4 month trip back. How many are going to Mars? Maybe? Yeah. Maybe?
Or younger.
Yeah, I think I would do that one. Think about this last question. So we're developing materials. We're going to put a station on the moon, an outpost on the moon. And eventually we're going to put an outpost on Mars. At some point, we're going to send people on a one-way trip to Mars. How many are taking that trip? I don't know if I would volunteer for that one either. But somebody's gonna. In your lifetime. Unimaginable. We're explorers. This is what we do. We're gonna go. I hope we've signed treaties. Questions? Space? Yeah.
So seeing some of these images, it's incredible. Just seeing how crisp and clear and how much they just really capture. How are we able to get those from those these spacecraft that are way out, say by Saturn, or super far from us, light years away from us? How are we able to get those images back from there to us? I never really totally understood how to do that.
Yeah, so we communicate with the spacecraft through radio waves, right? So it's basically like a walkie-talkie, right? Or, your cell phones are radio transmitters and receivers. So imagine having a transmitter and receiver on the spacecraft, and so you send a signal and tell it to take this picture, right? You're controlling remotely the cameras, the instruments on the spacecraft.
I see. And does that
And they'll send it back. So it has an antenna on it and it beams it back to Earth. And, if you're at Saturn, it takes, 8 minutes Earth Sun. Saturn is 10, so 80 minutes for a signal from Saturn, almost 72 minutes from Saturn back to Earth. So it takes over an hour traveling at the speed of light for a signal to get back to Earth. And double that if you want, send the signal and you got to wait, almost a little over 2 hours, 2.5 hours before you realize, okay, it took the picture. Or it did the command I wanted it to do, right? Yeah. So it is. It's weird. Time also becomes a factor now. Yeah.
Is there a pattern or a rhythm that you have noticed in how everything is constructed?
Yes, there is a great, also another classic short movie video that was made by Charles and Ray Eames, Eames, who were fantastic designers and writers and movie makers. And so if anybody's interested in fashion or furniture, look up the Eames. So they made this movie called The Powers of 10. So basically using these big numbers. And okay, what happens when we keep going out? It's kind of similar to what I just did here. And what you notice if you watch this, it's 9 minutes long, so you can find it, called The Powers of 10. You'll notice that there's a pattern of emptiness and richness, and then emptiness and richness as you go out and also as you go in. So they go reverse. They go smaller, smaller, smaller down to the atomic scale. And you get this undulation of this emptiness and then richness. So it is kind of interesting to see how that is kind of plays out. Good question. Any others? Yeah.
How do we know where our galaxy begins and where it ends? And if we were to leave our galaxy, would we enter another one, or would we be in a different?
Oh yeah, a great question. I didn't even address that. So we have interplanetary space, right, between the planets. Then you have interstellar space between the stars. And then you have intergalactic space between the galaxies. So yes, the edge isn't sharp for a galaxy. It looks sharp from the light that's coming from the stars, but it would basically fade to nothing. You would be outside of where stars are forming, or you could say the gravitational influence of the galaxy. Are you still held? Are you bound gravitationally? That's another way to define whether you're outside that galaxy or not. So yeah, so you would, and that's even bigger space, right, in between the galaxies. Yeah.
Thank you.
Uh-huh.
This is a little more lighthearted, but what are your opinions on the movie Interstellar? I think that movie is really cool, so
I thought Interstellar was an excellent movie. And The Martian, too, if you've not seen The Martian. I think it's recently on Netflix, so you can, if you've got an account, you can check it out. It's quite good. I thought Interstellar was very good. Of course, the idea here, if you haven't seen it, is they're, and I'm trying to remember exactly, but so they're getting close to a black hole, investigating a black hole. And black hole does weird things with time, too. So there's the example, if you travel really fast or you get close to something really massive like a black hole, time slows down compared to someone who's not near the black hole. So if you go around a black hole for a while and come back, you're aged differently. It's very strange. So they.
Does that even work? Do we know?
Well, we've not done the experiment, right?
Right.
Not with people. But amazingly, we've done it with clocks, very precise atomic clocks. We put one here on the ground, and we would put one in an airplane and fly it around for a few hours and bring it back together, and they're different by 20 decimal places. But we can measure it that accurately. So in that sense, yes, we've tested this.
Yeah.
I mean, this is Einstein theories of relativity, essentially working. And the famous example for theory of relativity working is that your cell phone wouldn't work without the theory of relativity. Your GPS, wouldn't work. Because we need the difference in gravity from us here on the Earth and the satellites orbiting Earth, the gravity is different. So time ticks differently. It's bizarre. Nature is bizarre. You don't have to invent bizarre. Nature is already doing it. And so in order for you to have your coordinates known very precisely, you have to account for the theory of relativity. If you didn't, your precision would start getting worse and worse and worse. Yeah. So Interstellar is a great movie. It also borders on a little bit on the metaphysical, maybe the spiritualness of things, and I thought that was great. I thought they did a really nice job sort of making that realistic. There's a couple scenes that were kind of goofy, but mostly I thought it was very good. Yeah, yeah. Any others? Questions? Well, this was a lot of fun for me. I could do this every week. And I kind of do with my astronomy class. And another shameless plug. So if you want to know more about these kinds of things, we do our star parties every month. And so the next one is this Friday over in the Weiser Patton building. So that's free for anybody, families to come. And clear, we'll open up telescopes for you guys to use.
Very good. Thank you.
Thank you.